Hello, I'm Norman Wildberger. Today we're going to move up to three-dimensional space and try to extend this metrical framework for geometry that we've been developing in the planar case to the three dimensions, still based on the fundamental algebraic notion of a dot product, which ultimately underpins all the discussion of the metrical issues in geometry in the linear algebra context. Okay, so we're working in three-dimensional space, and here is our standard representation of it. We have an x-axis, a y-axis, a z-axis. We have labels on all three axes. So the point 2, 3, 4, for example, is over 2 in this direction, over 3 in that direction, up 4 in that direction. So we can get to it by going 2 here, and then 3 here, and then 4 here. And we can picture it very concretely in terms of being a corner of a box that we create. The box here, or parallelepiped, has its sides all parallel to the three coordinate axes. This point down here, which is the projection of P onto the xy plane, will have the same xy coordinate, but the z coordinate is 0. Okay, so we want to investigate the idea of quadrants. How do we measure vectors in this kind of space? We want to talk about Pythagoras' theorem. We want to ultimately motivate the introduction of the dot product. So one way of doing that is to assume, first of all, that in our three-dimensional space, the two-dimensional Pythagoras theorem that we know and love holds. But we're going to assume that in a strong way, so that no matter what plane that we take, if we draw a right triangle in that plane, we expect this quadrants plus this quadrants to equal that quadrants. Now, we are biologically attuned to the idea that space is homogeneous, that the fundamental properties of space don't really depend if we rotate ourselves around inside it. So we're trying to build that into this theory here, but we still have to investigate whether we can actually do that in this coordinate framework, because we certainly are distinguishing certain directions as being more fundamental because we're basing our axes in those directions. All right, so let's suppose that Pythagoras works. Then the quadrants between O and P will be the quadrants between O and R plus the quadrants between R and P. Because this triangle right here, okay, is a right triangle. If we project P down perpendicularly onto the xy plane, then it makes, this line here makes a right angle with this line OR. So if Pythagoras is working, then this quadrants of this vector here should be the quadrants of this vector plus the quadrants of this vector. Now, in this particular situation, when this is the point 2, 3, 4, then the quadrants of OR, because this is just a planar vector now, we know about that, that's going to be 2 squared plus 3 squared. And the quadrants of RP, this vector here, well, that's just 4 up in the z direction, so its quadrants ought to be 4 squared. So we would expect that in this case, the quadrants of OP is going to be this quadrant, which is 2 squared plus 3 squared, plus this quadrant, which is 4 squared, for a total of 2 squared plus 3 squared plus 4 squared. All right, so what we're finding is that, assuming we have these two-dimensional Pythagorean theorems holding, that we expect that the quadrants of a vector is going to be given by exactly the same kind of formula as it is in the two-dimensional case. Namely, the sum of the squares of the entries of that vector. All right. So that's sort of consistent with our understanding of Pythagoras, and that's going to motivate our definition of the dot product and our use of the dot product. So motivated by Pythagoras' theorem, we are now going to introduce the metrical structure independent of any prior understanding of Euclidean geometry, just as we did in the planar case. So we're going to start with this definition of the dot product. The vector x1, y1, z1, dotted with the vector x2, y2, z2, is the number x1, x2 plus y1, y2 plus z1, z2. Two vectors dotted together give us a number. And not surprisingly, this is a symmetric bilinear form, meaning that it satisfies the familiar bilinear relations that v1 plus v2 dot v3 is v1 dot v3 plus v2 dot v3. And the other way around, very similar kind of story. And if we have a number, lambda, and we take the dot product of lambda times v1 with v2, and I forgot our little vector signs over here. There we go. Lambda v1 dot v2 is the same as v1 dot lambda v2, which is the same as lambda times v1 dot v2. And the symmetric condition is that v1 dot v2 equals v2 dot v1. All right, so we define this dot product. That's really the first thing that we do to start metrical geometry in three-dimensional space, before we have Pythagoras' theorem, before we have anything else. And now we define the two main real concepts in terms of the dot product, just as we did in the planar case. So we define the quadrants of a vector v to be v dot v. Call that the quadrants of the vector v. And we define perpendicularity between two vectors. We say that vectors v1 and v2 are perpendicular precisely when v1 dot v2 equals 0. So the fundamental measurement of quadrants is just as we expect. It's vector v dotted with itself. And the fundamental relation between vectors of perpendicularity is just given in terms of the dot product being 0. Now sometimes we want to refer to the quadrants between points. So we define the quadrants between point R and the point P to be the quadrants of the vector RP that joins them. And it doesn't matter if you take RP or PR, the quadrants of both of them is the same. So for example, the quadrants of the vector 1, 3, minus 2 is 1 squared plus 3 squared plus minus 2 squared, which is 14. The vector 1, 3, minus 2 is perpendicular to the vector minus 6, 4, 3 because the dot product 1 times minus 6 plus 3 times 4 plus minus 2 times 3 gives a total of 0. Dot product is 0, those vectors are perpendicular. And the quadrants between these 2 points, 1, 0, 5 and 2, 3, minus 1, is just the quadrants of the vector joining them, and we get the vector joining them by taking the difference between these coordinates. So that'll be 1, 3, and minus 6. And the quadrants there is 1 squared plus 3 squared plus minus 6 squared for, I guess, a total of 46. So pretty straightforward generalization of what we're doing in 2 dimensions. No surprises at all up to this point. So many more results and definitions follow the planar case. The first important thing, of course, is Pythagoras' theorem. And the statement is hopefully familiar. For any vectors v1 and v2, v1 is perpendicular to v2 precisely when the quadrants of v1 plus the quadrants of v2 equals the quadrants of v1 plus v2. And I'm going to give you also this alternate formulation, which is also convenient. So equivalently, quadrants of v1 plus quadrants of v2 equals quadrants of the difference v1 minus v2. And there's sort of 2 diagrams that we can associate with these 2 equations. So here we have a vector v1 and another vector v2, which we're drawing here, emanating from the head of v1. And these are perpendicular here. This is the vector v1 plus v2. So we have a right triangle here. In that case, the quadrants of v1 plus the quadrants of v2 will be the quadrants of this third side, the hypotenuse v1 plus v2. Here is a diagram that sort of illustrates this version of it, where we think of having 2 vectors emanating from the origin. So here's v1 and here's v2. And here's the difference, v1 minus v2, going from the head of V2 to the head of V1. And now the right aspect, the perpendicularity between V1 and V2, is manifest in terms of this equation, that the quadrants of V1 plus the quadrants of V2 equals the quadrants of V1 minus V2. So they're just slightly different diagrams the way they're situated. So maybe you could say different interpretations of the meaning of these formulas. And your exercise, first one today, is to check that the proof still works. That the proof that we wrote down for the planar case is verbatim exactly the same here, and still works exactly as before. So we have to make sure that Pythagoras is still holding for exactly the same reason as it did before, a purely algebraic derivation, the equality between this kind of perpendicularity and this expression between three quadrants. Now, what else did we do with the dot product in the two-dimensional case? Well, one thing that we did is we defined the idea of a linear functional. And that was really just having a look at this dot product v dot w and imagining that one of the vectors, say v, was fixed and the other vector w was sort of variable. So we could then say that this is a functional f sub v of w. So it's something that inputs the vector w and outputs a number. So it's a function, we can think of it as a function that's defined on our vector or linear space. And we can picture that in the same kind of way as we did in the planar case, but it's just a little bit different now because we have more room. So here's a vector v. If we look at this functional, then the places where it's going to be 0 it's going to be all those vectors which are perpendicular to v. Now in three-dimensional space, if you have a vector like this one here, the vectors which are perpendicular to it are, let's say this is the origin, are all the vectors that are emanating from the origin that are perpendicular to it. And there's will be a whole family of them in all these directions. Of course, all multiples of these too. So this will actually sweep out a plane now, not a line as in the planar case. All right. So that's what we're visualizing here in red. This is the plane of vectors w for which this functional is 0. In other words, for which the dot product v and w is 0. In other words, those vectors w which are perpendicular to v. So any vector in here, say w, is perpendicular to the vector v. And then here, this shifted plane is the plane consisting of vectors w, which are having the property that f of v of w equals 1. Or in other words, v dot w equals 1. Yeah. And of course, the bigger v is, the closer these planes are to each other. So very similar to the planar case where we had lines, but now we have planes that essentially determine the functional. And if we want other values of the functional, well, it's all kind of linear. So the function's 0 at this plane, 1 at this plane. If we go an equal amount in the same direction, we get to where the function has value 2, and then 3, and then 4. If we go in this direction, it's -1, -2, and so on. So the level surfaces are planes, and they all have this normal vector v. Each of the planes is perpendicular to this vector v that defines the functional. All right, so now we get the natural connection between planes in three-dimensional space and these fundamental linear equations that have played a big role in the first part of the course. If we have an equation like ax plus by plus cz equals d, that defines a plane in three-dimensional space. In other words, those vectors x, y, and z that satisfy the equation give us a plane. Now we have the possibility of interpreting that plane geometrically. This is then a level surface for this linear functional which has vector ABC as the normal. So it's f of ABC applied to x, y, z. And I remind you this functional is just taking the dot product of those vectors, giving us ax plus by plus cz. What we're saying is that this plane is defined as a level surface for this linear functional. And so it has normal vector n, which is a, b, c. In other words, the coefficients of x, y, and z now have very specific significance. They are forming the normal vector to the plane. There's the plane, ax plus by plus cz equals d. There's the vector ABC. The plane is perpendicular to the vector. In particular, if we change this right-hand number d, then what happens to the plane is it moves in this direction, but it doesn't change the fact that it's still basically perpendicular to the normal vector. So the effect is just to move it around like this. All right, so our understanding of planes in three-dimensional space is now very parallel to the understanding of lines in two-dimensional space. And if you're coming from high school, this may be a little bit of a different orientation. We're thinking often of lines and planes as being sort of different kinds of objects, but they're very parallel here. In both cases, we're trying to think of both of them as defined primarily in terms of this normal vector. Given a line or given a plane, your first question should be is what's the normal vector? Right. That's defining the orientation of the plane. And then the right-hand side is telling you exactly where it's situated, given that it has a particular orientation. All right, so what else did we do? Well, we talked about projections of one vector onto another. We can do exactly the same thing here in three dimensions. The story is exactly the same. We have a vector v, we have a vector w in three-dimensional space now. We can still talk about the projection of w onto v. This vector u, all right, so that vector u is the projection of w onto v, where we're going down perpendicularly. And exactly the same derivation, you can check, gives us exactly the same formula, that the projection is v dot w over v dot v times v. So the actual vector w that we're acting on only appears once in the formula in the numerator there. So it's still a linear function of w. All right, so here's a few exercises just to practice getting a little bit used to three-dimensional space, working with these vectors with this metrical structure now. I know you already had experience with three-dimensional vectors in the first part of the course. Now we're adding a little bit to that because we're making some measurements, starting to make measurements, and using this dot product for various things. All right, so first exercise, we've got three vectors, v, w, and u. So just compute a few things. If I say the quadrants of v, the dot product of v with w, the projection of u onto w, the projection of w onto u, the projection of u plus w onto v, and perhaps the plane through v normal to u. Next exercise, show that the formula that we derived in the planar case for the projection still holds here. A kind of matrix formula. We're interpreting all of these vectors now as column vectors or matrices. Then show that for any v and w, p of v of w is given by this formula here. V times v transpose, so that's a column vector times a row vector, so that's actually a matrix, divided by v transpose times v, that's actually a number, and w is just the column vector or the 3x1 matrix. And the fourth problem, something to do with Pythagoras, shows that the triangle with vertex points 1, 2, 4, 4, 3, 2, and 5, 4, 4 is actually a right triangle. So in other words, verify that two of the sides are perpendicular, and verify that Pythagoras' theorem holds. So everything that we've done so far is parallel to what we've done in the planar case, and this now introduction to spheres is similar. We're just going to extend the idea of circles and the discussion of circles to three-dimensional case and talk about spheres, but spheres centered at the origin. So here's our three-dimensional space, x, y, and z coordinates. Here's our origin. Here's the kind of sphere that we're talking about, called S. And our natural starting question is, what should our definition be of a sphere? And just as in the circle case, I'm going to offer you two possible definitions. One is a kind of traditional, or somewhat traditional definition, and a somewhat more advanced or maybe more modern definition. So our first definition would be that a sphere is an equation of the form, say S, v dot v equals k. Okay? V is a vector. V dot v is the quadrants of that vector. So we're talking about the equation that the quadrants of the vector is k. And specifically, in terms of a vector v having coordinates x, y, and z, the quadrants of v will be x squared plus y squared plus z squared, so this is the equation of the sphere. And we all recognize that's a familiar Euclidean kind of equation for a sphere centered at the origin. Looks like this. And so we're saying that that vector v, which lies on the sphere, has exactly quadrants k. And the sphere consists of those vectors that have that property. All right, that's all well and good, but now we recognize also that that's a sort of quadratic definition, and here's now a bilinear definition, which is in some ways a little bit more flexible, a little bit more general, a little bit more sophisticated, and a little bit more powerful. In fact, actually quite a lot more powerful, to be honest. All right. So we're going to slowly try to get you to move up in your thinking, right? From this kind of thinking about what a sphere is to this kind of thinking about what a sphere is. Although they're of course still very closely connected. And we can still draw the picture of the sphere this way. All right, so what's our bilinear definition? It's that a sphere is an equation of the form v1 dot v2 equals k. It's an equation involving two vectors, not one. And in fact, it's exactly the same kind of equation as that for a circle. It's just that now the interpretation is that the vectors are three vectors instead of two vectors. And this dot product is the dot product in 3 dimensions rather than in 2 dimensions. So we can see that really we could extend this to n dimensions without any difficulty at all. Just a question of making the vectors longer and making the dot products longer, and everything is going to be pretty well much the same. In terms of specific coordinates, if v1 is the vector x1, y1, z1, and v2 is the vector x2, y2, z2, well, then this dot product is this thing here, x1, x2, plus y1, y2, plus z1, z2, and the equation of the sphere is then that equals k. So when we think about the sphere in this way, the only real question about a vector is, does it lie on the sphere or not? When we think about the equation this way, there's more to think about. Because if we take a vector v1, which is not lying on the sphere, we can still ask about all the vectors v2, which satisfy the equation v1 dot v2 equals k. We can still look for pairs of vectors v1, v2 that satisfy the equation. And now what we're really doing is we're saying, well, okay, we're looking at those vectors x2, y2, z2 that lie on exactly this plane. This is now a plane whose normal vector is x1, y1, z1. There's v1. Then this will be a plane that, well, v1 is bigger than the quadrants of the sphere. Then we can expect that the perpendicular plane will cut the sphere typically, at least approximately, and we might even get a sort of a circle in which it cuts it out. So this plane here is what we should call v1 perp with respect to s. Those vectors v2 that are perpendicular to v1 with respect to s, meaning that this equation is satisfied. So we get the same kind of polarity as we did in the two-dimensional case, but now crucially the duality is between a vector and a plane. Here we have a sphere, we have a vector outside the sphere. Its dual is going to be a plane that meets the sphere. And the closer the vector comes to the sphere, the closer that dual plane is to becoming a tangent plane to the sphere at that very point. And if the vector v goes inside the sphere, well, then the dual plane goes outside the sphere. So it's a little bit, that's a different kind of geometrical story. It looks different because we have a dual plane now, not a dual line. And the plane is richer. It meets the sphere now in a circle often, not just in a pair of points. Okay, so this is sort of just an introduction to this. There's lots to be said about spheres. In fact, there's a lot to be said about three-dimensional geometry in general. Okay. Three-dimensional geometry is a much neglected subject in 20th century mathematics, sadly. For some strange reason, despite the fact that it's the mathematics of the world in which we live in, actual three-dimensional geometry has almost dropped by the wayside. There's a little smattering of it here and there in linear algebra courses, but not very much and not very well done, I have to admit. All right. So we're going to try to rectify that a little bit, and this is certainly a good way to sort of start thinking about the geometry of three-dimensional space metrically. So we're going to come back to three-dimensional space. There's going to be quite a lot more that we can say just in the context of linear algebra. So this has been something of an introduction to some of the main ideas. Next time what we want to do is we want to enlarge our view in a different direction. I've been talking a lot about the dot product as being rather flexible, and that there's these other dot products that are out there that really have the same story as the dot product that we've been talking about. In particular, there's this relativistic dot product that I keep on mentioning. Okay. This is a very crucially important object for 20th century physics. And next time we're going to have an introduction to the relativistic dot product and some geometry associated with that. That's a topic that's almost never discussed in linear algebra courses, despite the fact that in 20th century science, the geometry of relativity was an absolutely key development. So it's something that we have to catch up. We have to make some effort to catch up. Right. So next time, an introduction to relativistic geometry via linear algebra and dot products. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.